as a steam turbine receives steam steadily at 10 bar with an enthalpy of 3000 kilojoule per kg and discharges it at 1 bar with an enthalpy of 2700 kilojoule per kg. The work output is 250 kilojoule per kg. The changes in kinetic and potential energies are negligible. The heat transfer from turbine casing to the surroundings is equal to A 0 kilojoules, B 50 kilojoules, C 150 kilojoules, D 250 kilojoules. The solution to this problem is given from the steady flow energy equation, which is stated as Q minus W is delta H plus delta KE plus delta PE. Because changes in potential energy is negligible, it can be neglected. Because the changes in kinetic energy are neglected, it can be made 0. It is given that work output is 250 kilojoules. That is, W is equal to plus 250 kilojoule per kg. And change in enthalpy delta H is given as H2 minus H1, which is equal to 2700 kilojoule per kg minus 3000 kilojoule per kg. It becomes minus 300 kilojoule per kg. Whenever we are writing delta H on the right hand side of SFAE, it is always final enthalpy, that is exit enthalpy minus inlet enthalpy. Substituting these values in the above equation, we get Q minus of plus 250 is equal to minus 300, implies Q is equal to minus 300 plus 250. It becomes minus 50 kilojoule per kg. Minus sign indicates heat must have been rejected from the turbine to the surroundings. Doing another problem in the same model, which was given in GATE 2001, which is stated as a small steam vessel in bracket perfectly insulated and doing no shaft work causes a drop of 0.8 kilojoule per kg in the enthalpy of steam from entry to exit. If the kinetic energy of the steam at entry is negligible, the velocity of steam at exit is A 4 meters per second, B 40 meters per second, C 80 meters per second, D 120 meters per second. Writing steady flow energy equation, because the vessel can be considered as a steady flow open system, that is Q minus W is equal to delta H plus delta KE plus delta PE. Changes in PE are neglected because he has given perfectly insulated QE is 0, no shaft work done, W is 0, which means minus delta H is equal to delta KE. Decrease in enthalpy or enthalpy drop is equal to increase in kinetic energy, that is minus 0.8 into 10 cube. We have to convert enthalpy in kilojoules into joules. Then only units on the right side and left side will get satisfied. V2 square by 2 minus V1 square by 2. That is a change in kinetic energy in joule per kg. Because inlet velocity is neglected, V1 is taken as 0. Therefore, it is minus of minus, because H1 minus H2 is equal to 0.8 into 10 cube is equal to V2 square by 2, implies V2 is equal to square root of 2 into 800, that is 4 into 1040 meters per second. B is the answer. Because in the SFE right hand side is always is equal to final minus initial. Now let us consider a problem on the application of the second law of thermodynamics. A heat engine having an efficiency of 70% is used to drive a refrigerator having a COP of 5. The energy absorbed from low temperature reservoir by the refrigerator for each kilojoule of energy absorbed from high temperature source by the engine is A 0.14 kilojoules, 0.71 kilojoules, 3.5 kilojoules, D 7.1 kilojoules. This problem was given in GATE 2004. Now let us represent pictorially the problem given. A heat engine is driving a refrigerator. Refrigerator should run in the anti-clockwise sense, whereas heat engine should run in the clockwise sense. The heat supplied to the heat engine is given as 1 kilojoule. The heat is being rejected from the heat engine, whereas the refrigerator will absorb Q absorbed from low temperature and rejects heat to the high temperature. The source is supplying heat to the heat engine. To the sink, heat is rejected by the heat engine. He has given that thermal efficiency of the heat engine is 0.7 or 70%, which is defined as W divided by heat supplied. Implies W of the heat engine, work output of the heat engine is equal to heat supplied to the heat engine, that is 1 kilojoule into 0.7, so many kilojoules. From the COP formula of the refrigerator, which is given as 5, we can write that Q absorbed by refrigerator from low temperature divided by, now the COP of the refrigerator is given as 5 is equal to Q absorbed by low temperature reservoir divided by work input, whereas the work input is 0.7 kilojoules, that is Q absorbed by low temperature divided by 0.7. So Q absorbed by low temperature is equal to 5 into 0.7, that is 3.5 kilojoules. C is the answer. In the same GATE 2004 paper, another problem is given as a solar collector receiving solar radiation at the rate of 0.6 kilowatts per meter square transforms it to the internal energy of a fluid at an overall efficiency of 50%. the fluid heated to 350 Kelvin is used to run a heat engine which rejects heat at 313 Kelvin. If the heat engine is to deliver 2.5 kilowatts power, then minimum area of the solar collector would be A 8.33 meter square, B 16.66 meter square, C 39.68 meter square, D 79.36 meter square. So let us indicate the problem in a pictorial manner. A solar collector is receiving a heat of 0.6 kilowatts per meter square. Therefore, total heat received is equal to 0.6 into area of the plate. So many kilowatts, because it is transforming the total energy received into internal energy of the fluid with an efficiency of 0.5. The internal energy of fluid increased is equal to 0.6 into AP, that is the total energy received, into half, that is transformation efficiency. This is the internal energy of the fluid increased, because of which the fluid temperature is increasing to 350 Kelvin. Therefore, the heat supplied to the heat engine is equal to .6 into AP into 0.5, so many kilowatts. The thermal efficiency of heat engine is equal to power output divided by heat supplied, that is power output divided by 0.6 into AP into 0.5, where AP is the area of the plate. The area of the plate will be minimum only when the thermal efficiency of the heat engine is maximum. That is when the heat engine operates on Carnot cycle, or when the heat engine is Carnot heat engine, which is also known as reversible heat engine. Thermal efficiency of the Carnot heat engine is equal to 1 minus TL by TH, which are given as 1 minus 313 by 350. Both the temperatures are in Kelvin. Therefore, The equating the thermal efficiency to the above formula, that is P divided by 0.6 into AP into 0.5, where P is given as 2.5 kilowatts. 2.5 divided by 0.6 into AP into 0.5. Therefore, minimum area of the plate will be 2.5 divided by 0.5 into 0.6 whole divided by 1 minus 313 by 350, which gives the area of the minimum area of the plate in meter square, which should match with one of the options given along with the problem. Considering another problem regarding the Mach number, an aeroplane is cruising at a speed of 800 kmph at an altitude where the air temperature is 0 degrees centigrade. The flight Mach number at this speed is nearly A 1.5, 0.254, 0.67, D 2.04. The Mach number of flight is defined as velocity of flight divided by velocity of sound under local conditions of temperature. Velocity of flight is given as 800 into 1000 divided by 3600 after converting into meters per second, whereas velocity of sound in air is given as square root of gamma RT, that is equal to 800 into 5 by 18 divided by square root of gamma of air is 1.4, R of air is 287 joule per kg Kelvin, and the temperature of air is 0 plus 273 Kelvin, which results in the answer of 0.67, that is subsonic speeds of flight, because Mach number is less than 1. I shall consider another problem on throttling. When an ideal gas with constant specific heats is throttled adiabatically with negligible changes in Ke, that is kinetic energy, and Pe, that is potential energy, then A, delta H is equal to 0, delta T is equal to 0. B, delta H is greater than 0, delta T is equal to 0. C, delta H is greater than 0, comma, delta S is equal to 0. D, delta H is equal to 0 and delta S is greater than 0? The answer is given like this. Because the process is throttling, during every throttling process enthalpy remains constant. Therefore, delta H is equal to 0. Then coming to the temperature changes, because working fluid is ideal gas, for ideal gas mu is 0. What is mu? Joule-Thomson coefficient. Because Joule-Thomson coefficient is 0 for ideal gas, there would not be any temperature changes when the ideal gas is throttled. That is, delta T is equal to 0. And coming to the entropy changes, because the process is irreversible adiabatic process, throttling is an irreversible adiabatic process, delta S must be greater than 0, because entropy would always increase during every irreversible adiabatic process undergone by the system. Therefore, there are two answers, that is namely A and D. Considering another problem in which the two cycles are coupled in series, the problem is like this, which was given in the previous GATE examination. For two cycles coupled in series, the topping cycle has an efficiency of 30% and the bottoming cycle has an efficiency of 20%. Then overall combined cycle efficiency is A 50%, B 44%, C 38%, D 55%. Representing the problem in the pictorial form, we see that the topping cycle is represented as T. The heat rejected by the topping cycle is given to the bottoming cycle, which is represented by B. Both are heat engine cycles. If Q is the heat supplied to the topping cycle, then work output of the topping cycle will be given as 0.3 into Q. Then the heat rejected would be Q minus 0.3 Q according to the first law, that is 0.7 Q. This is the heat supplied to the bottoming cycle, whose work output can be calculated as work output of the bottoming cycle is equal to heat supplied to the bottoming cycle, that is 0.7 into Q, is equal to into thermal efficiency of the bottoming cycle, that is 0.2. Then overall thermal efficiency of combined cycle is work of the topping cycle plus work of the bottoming cycle divided by total heat supplied to the topping cycle, that is Q, which is given as 0.3 into Q plus 0.7 into 0.2 into Q divided by Q, which is resulted as 0.3 plus 0.7 into 0.2, where Q gets cancelled. This is the final answer.